Hello and welcome to our video regarding citric acid production by Aspergillus niger. Our team is composed of Darren, Debbie, Linda, and myself, Jason. So let us begin with a brief introduction of citric acid. Citric acid, which is also identified as 2-hydroxypropene 1,2,3-tricarboxylic acid, is a weak organic compound that could be found in nature and in the citric acid cycle. Citric acid has various applications from the food and beverage industry as acidulants, preservatives, buffering agents, and emulsifiers, cosmetic industries as exfoliants and antioxidants, and the pharmaceutical industry as preservatives, excipients, and antioxidants. With its various applications, citric acid is required in a high demand, and by 2023, it is estimated that the citric acid industry will be worth $3.2 billion. Meanwhile, the production of citric acid can be achieved through chemical synthesis, that is obtained from citrus fruits although in small amounts, or microbial fermentation with fungi fermentation, which is the commonly used method in the industry. In this review, we are going to discuss citric acid production through bacterial fermentation method by utilizing Aspergillus niger. Aside from Aspergillus niger, there are other alternatives from other fungi, bacteria, or yeast. Although there is no citric acid production based on bacteria due to its non-compatibility and low yield, there is a possible alternative with yeast, but with an undesirable byproduct. Hence, fungi such as the Aspergillus niger is deemed superior to other alternatives due to its productivity, robustness to extreme environments, economically efficient, and has some compelling polymer-degrading enzymes. Since we are using a live microorganism, it is important to understand its biochemical synthesis and accumulation pathway. As you can see in this graph, the synthesis and accumulation of citric acid is heavily dependent on the regulation of both glycolysis and the tricarboxylic acid cycle. The oxaloacetate has a huge role in the reaction process for the citric acid production as a driving factor for the enzyme affinity with acetyl-CoA. For this production and accumulation of citric acid to occur, fermentation parameters are important for the upstream processes. Molasses are a popular substrate used for the citric acid production when compared to other carbon sources or pure glucose or sucrose. Molasses is inexpensive and contains glucose and sucrose for the Aspergillus niger fermentation. Waste from agriculture or agro-industry can be utilized as a substrate for fermentation with lower cost and has environmental benefits, although some may need pre-treatment. Aside from the use of microbes and substrates, the environmental factors are also detrimental, such as carbon source, where glucose and sucrose are preferred. Phosphorus is also preferred at a lower concentration. The next factor is nitrogen, which plays a role as a cofactor, followed by trace elements which can affect the production and growth. A temperature between 25 and 30 degrees Celsius are the most suitable for fermentation, and an oxygen aeration of 25% is also preferred. And lastly, pH during the initial and final stages affect the production and recovery. For the strategies of fermentation, submerged fermentation is the most commonly used method. This method produces less yield than the others, undesirable fumes, but is simpler, easier to scale up, and easier to operate. Solid-state fermentation is found in Japan with a higher yield, but has poor heat and oxygen transfer rate, hence the substrate is not fully utilized. Surface fermentation is performed on steel trays in a fermentation chamber, also has a higher yield, but is labor-intensive and takes a long time. After fermentation, downstream processing has to be conducted. The most commonly used method is precipitation. It is simple, but generates unwanted waste like gypsum. Other alternative methods such as solvent extractions are also used for generating less waste. In both of these methods, there is crystallization for citric acid recovery in precipitation by using a high temperature, while in solvent extraction using extrusions. New strategies for downstream processing are also studied. In adsorption, there is an application using Ralex 425 resin as absorbent and methanol as desorbent, where 99% purity and 95% recovery of citric acid can be achieved. And in electrodialysis, it involves electrochemical separation. The membrane is electrically charged, and an electrical potential difference is utilized for the separation of ionic species that comes from the aqueous solution. In citric acid production, Aspergillus niger is the most suitable microorganism for fermentation. Targeting the correct pathway and using the best parameters is crucial for a high-yield production. Although the submerged fermentation is upscalable, surface and solid-state fermentation can have a higher yield and should be further studied. And for recovery, Advanced technologies such as adsorption and electrodialysis can be employed for less waste and high recovery.